All right, so this is kind of, you're getting to the part where we have done all the statistics we need to get to like the big chunk of what statistics is used for. The first thing is called confidence intervals. So I've said all along that we go do a sample and we try to use that information to predict for the entire population, okay? What statisticians want to do though is they never want to back themselves into a corner. So if I say that I surveyed 100 FSCJ students and I don't know, 45% of them like their favorite ice cream is vanilla, I don't want to go and tell the bosses that I'm 100% confident that 45% of all FSCJ students do that, right? I only sampled 100 and I'm trying to predict what would happen when we asked all 6,000 or 7,000 that take math classes or whatever. So I'm using a small sample to try to predict what's happening in the population. If I go tell the bosses that it's 45% and it comes back at 40%, well, maybe they ordered too much vanilla ice cream when they should order some more chocolate or whatever, you know, different scenario there. It costs money. So as statisticians, we are the people that do the math and then go tell the bosses what they should see in the math, basically. So what we want to do is something more like we walk in there and say something like, we're 90% confident that if we were to actually survey all FSCJ students, that somewhere between 42 to 48% of them are going to like vanilla ice cream more than any other flavor. Okay, so we give a range based on that, and that is called a confidence interval. Well, I said I'm 90% confident, and that 90% confident has to do with this. Actually, I'm going to go ahead and show you that because that's this is something that will help us. We may make a chart for this to make your life easier too, but so what the confidence interval has to do with, this is the math that we've been doing. This is a normal distribution. You've seen this. So like in my example just a second ago, I used a 90%. So what that is actually saying is, what is 90% of this thing shaded, okay? Remember, my mean is in the middle. That's what we're trying to guess. So, I'm trying to guess that it's like 45% ice cream, and let's say our standard deviation is 2 or whatever. So actually 42 to 48 is a pretty good guess there. So my mean was 45% with a standard deviation of 2%. We could probably say we're 90% confident that it is somewhere between 41.7 and 48.3. So 42 to 48 is a pretty good guess off the top of my head there. So this is what that 90% means. The 90% is how much of this curve is shaded, okay? So what happens here is if I am 90% confident, I actually have a smaller interval because there's a 10% chance I'm wrong anyways, right? So if I tell you I'm 90% confident, there's a 10% chance I'm wrong. But if I tell you that I'm 99% confident, I am going to make my interval bigger. It's 99% shaded now. So if I say that I'm 99% confident, I'm going to give you a bigger interval, and now it's between 40 and 50, okay? So instead of being between 42 and 48, it's between 40 and 50. So if I ever say that I'm 99% confident about something, I give myself a huge margin of error is what they call it. So that is what this whole section is about, these confidence intervals and how to build them and the different concepts between them. One of the big ones that I just went over right there is as my confidence level increases, my confidence interval also increases because I want to make sure that I'm right. If I'm, like I said, if I'm 90% chance, there's a 10% chance I'm wrong. But if I say I'm 99% confident, then I want to give myself a huge margin of error to make sure I'm right. Okay. So this first one is the most annoying one in probably the whole section right here. Probably one of the most annoying ones in the whole class. This one, the best way to do statistics, I think I said this on week 1, is to do samples over and over and over and over and over again, okay? So if on this example right here, it gives you 20 different samples. It says the mean of the population is 90, so we know the answer. Usually we're trying to guess what the mean of the population is, okay? But we're kind of doing computer math here, and we have the actual mean. So the mean is 90. So we go do the first sample, and the average of that one is 90.6, okay? And if you do an 80% confidence level, we would say there's a 20% chance I'm wrong, so I have a super small margin of error. So it would be I'm 80% confident that it's between 89 and 92, okay? But then I'm 95% confident that it's between 88 and 93, okay? So I have a little bit bigger range there because I only have a 5% chance that I could be wrong. So we do one sample like that, and this one just generates 20 different samples. And we want to know how often, the first question is how often, this is the little chart, so that red line and the blue line are the 90. We actually know the end answer on this. Usually we're trying to guess what the end answer is. But I want to see how many of these 20 samples got it right. How many of these 20 samples hit the 90, okay? So all you got to do is count for A and B. I told you all this was a super hard one, and now it's going to be very easy. So there's 20 different samples. So if I count, I'm not counting. I'm going to cheat and click solve. So there are 17 of the 80% ones. I was trying to find the one that hits right here. 17 of the 80% ones. So there's 17 of these that hit the red line, and there's 18 that hit the blue line, okay? The reason that there's always going to be more on the blue line is because when my confidence increases, my interval is going to increase. So if I look at this sample right here, this is sample number 4. In sample number 4, scroll back over here, the 80% was between 90.5 and 93.5. So 90 is not included. 90 would not be in the middle of that, right? But the 95%, if I say I'm 95% confident, I give myself a big margin of error. It's between 89.7 and 94.3. So you can see by this picture right here, of this one right here, it just doesn't quite get to that 90 as this one does. So the higher the confidence, the bigger the interval, the more likely you are to actually find the true mean. All right. So the counting part is easy. The hard part is down here at the bottom, because sometimes it's one answer, sometimes it's two, sometimes it's none. So we'll go through each of these. Since sample 19 and 20 are drawn from the same population, the center of 95% confidence interval for sample 19 must be the same for the sample 20. No, every time I do a sample, I am sampling different people, okay? I go ask 100 people on Monday, then I go ask 100 people on Tuesday, then I go ask 100 people on Wednesday. I'm not going to ask the same people the same question over and over again, because then I get the same number. So that is no, they are different. And you can look up here when it says sample 19, sample 20, sometimes they do sample 1. Look up here. These are not the same numbers, right? They're not the same numbers. All of the 95% confidence intervals should be the same as each other. No, we are asking different people, so all the samples should be different, okay? For some of the samples, the 85% confidence interval is included in 95%, while others it is not. This is actually every single one of these fits inside of here. Okay, so this one would fit inside of this one. This one would fit inside of this one. This one would fit inside of this one. Because what I'm saying is, if I'm 80% confident, my interval is going to be like this. If I'm 95% confident, my interval is going to be like this. So it's based on the same center. The center does not change. Does that make sense? So like 80% confidence interval, small margin of error. 95% confidence, big margin of error. So every single time, the center of these are going to be the same, and the smaller one is going to fit inside the bigger one, okay? So that actually should be every single one fits in there. And the last one is true. The center of the 80% confidence interval for sample 1 is 90.6. Again, if it says what sample it is, scroll up there and look. The center is 90.6. Yeah, that's probably true then. Because the center of the confidence interval for the population must be the sample mean. Yes, we're trying to guess based on a sample that it should be the population. Let's go through one more scenario here. So this one is 75%, 90%. There are 13 that hit it at the 75% and 16 that hit it at the 90%. So for some of the sample, the 75% confidence interval included in the 90%. For others, it's not the case. I just went over that one. That's not true. Every single 75% does fit inside the 90%. The sample means for the sample 19 and 20 are different. So the center of the 90% interval for the sample 19 is different from the sample 20. Again, look at sample 19 and 20. The centers are different. We ask different groups of people, so the average will be the different for those groups of people. It is not surprising that some of the 75% confidence intervals are different from other 75% confidence intervals. Each confidence interval depends on its sample, and different samples may give different confidence intervals. Yes, we did 20 samples of 20 different people, so we should get 20 different numbers. It'd be coincidence if we got the same thing. We would expect to find more 75% confidence intervals that contain the population mean than 90%. Well, look at your number right here. 75% is 13 and 90 is 16. The bigger number will always include more because it's wider, so it's going to hit it more often, okay? So this should be, we find more 90% confidence intervals hit it. I think that hit about every variation of those examples there. 1920. There's that one I just said. For each sample, the 80% confidence interval. No, we did that one. Okay. Yeah, see, I already went over all those. Right here, I guess this is the opposite of what I just said. We would expect to find more 90% intervals that contain the population mean than 75%. Yes, the 90% number will always be bigger because it's wider, okay? That one is not fun because of the different variations, and you got to choose all that are true. So sometimes it's one, sometimes it's two, sometimes it's none. I do have examples up on the website, all those different things. I should have probably screenshotted some of these, but I didn't. I'll try to put some notes up there. Okay. So now we are going to actually construct a confidence interval. So it starts easy and gets a little harder. But I like the take a sample button here. You work a chain taco restaurant and wants to estimate the population mean of the wait times in the drive-thru for all customers. To do so, you select a random sample of 40 of the chain's drive-thru customers and record the wait time for each of those. Assume it's known that the population standard deviation is 2.79. Based on your sample, follow the steps for a 99% confidence interval. So that's the big number that we're going to need there, 99%, okay? So we do a sample that we get to generate. Like, we're not going to actually go sit outside Chick-fil-A and time them because we don't got time for that. But this simulates that. So 40 customers took about 3.94 minutes with a sample standard deviation 2.39. You start by just filling out this chart. Super easy. Sample size is how many people you asked or surveyed or whatever, okay? The point estimate is the mean. The point estimate's the mean. That's what we're basing everything off of. That is called a point estimate because that's our estimate for the population, okay? That's where we're starting at. That's going to be the center of our interval. And then the population standard deviation, make sure you get the population one, not the sample one. So we want this one, 2.79. Critical value. This is the one hard thing to find on here. It's easy on this one, but it gets a little harder in just a second. The critical value is this number right here, like 99%. So remember what we did in our picture. Oh man, did it go away? The 99% is basically saying what z-score goes along when this is 99% shaded. So what z-score do I have right here when it's 99% shaded? It'd be 2.56, so 58, 2.58. Or 2.576, yeah, okay. So the 99% confidence interval, the z-score that goes along with that is 2.576. Okay. Now we click compute, and it finds our standard error. Our standard error is based on our data. We don't have to find that or anything right now, but you don't ever have to find that, but just to talk about it for 2 seconds. The standard error is based on our data, how big our standard deviation is. If we had a big standard deviation, it'd make our standard error bigger. The margin of error is actually this critical value, the z-score times our standard error, I believe. Let's try it. 2.576, which is trying to remember the formula off the top of my head. 2.5, come on, click. 2.576 times 0.44. Yes, okay. So yeah, what they do for the margin of error, and this is the same margin of error that they use if you ever see a voting thing or anything, or they say this candidate is 48% plus or minus 2% margin of error. They always put that. Same kind of concept there, that if I take the margin of error and add it to my point estimate and subtract it, that gives me a range. Okay, we'll do that in just a second. But the standard error comes through based on our numbers from our sample, and then we do that times the critical value because that's going to make it 99%. Okay. So our confidence interval is this number right here. You can actually go to the calculator. 3.94 plus or minus 1.13. Okay. If you hit the plus or minus button, it's going to do that. What that's going to do is 3.94 plus 1.13 and 3.94 minus 1.13. It's easier just to do it that way, right? So, oh no. So we click over here, and now we build the interval, 2.87, 5.07, and we get our answer, okay? So this interval, we would say we are 99% confident that this drive-through wait time is between 2.87 minutes. The average drive-through wait time is between 2.87 minutes and 5.07 minutes, okay? So now we can go tell the bosses, and we're 99% sure there, and they can decide, okay, we need to get that 5 under, like we need the top end to not be 5% or 5 minutes. Wait, y'all with me? Not so bad so far, right? This is all it is, this section, basically. So we'll continue to do these, skim through these. I'd probably need to take some notes or put some stuff on that sheet there. It's So this one's about a medical group and a heart valve patient, how long the surgery is for a heart valve patient. We click take a sample. It's 32 people that we are sampling. 32. Our point estimate is the average, 4.38. The population standard deviation is 1.92. Critical value, what are we doing? We are doing, go back up here. Oh, it says it right here, I guess. 99% confidence interval. Okay, here's our first trick on this. It doesn't have the 99% next to this right now, right? Okay, I know that the answer is right here. I'm trying to figure out what this number is right here. If I have 99% on the inside, how much do I have on the outside? 1%, right? But there are two tails, right? So how much is on this side right here? 0.5% here and 0.5% here. So that is how you figure out which one to do. This is 0.05. Well, it's 0.5%, so it would be 0.005, right? Yeah. So what you can do is you can do 1 minus, well, let me put this first. Let's put a division. 1 minus 0.99 and divide it by 2. So the 1 minus tells us how much is on the outside, and you divide it by 2 because it's two tails. There's one on the right side, one on the left side. So you do 1 minus the confidence level divided by 2, and that will tell you exactly which one to use. So I'm using the 2.576. Okay. So we click compute. We come down here and we say, okay, our margin of error, let's go ahead and put that in the calculator. Again, all this is really doing is 4.38. Why can I not hit the right buttons? 4.38. This is doing 4.38 plus 0.88 and 4.38 minus 0.88. That's what you do is you take the middle number, you add the margin of error and subtract the margin of error. But this just does it all at once. So 3.5, 5.26. And then this thing, a new thing on this one is this red dot. This red dot for the point, diamond red right here, enter the medical group's claim. So they claimed it was taking 5.65 hours. But when we did our data, we're 99% confident that the surgery only takes between 3.5 and 5.4. So I'm surprised that the medical world is trying to scam us out of more money, right? So they are actually charging patients more money based on the average than they're actually being in surgery. They're charging for 5.7 hours, and we're only getting surgeries between 3.5 and 5.4 hours, okay? So we would say, yes, it does contradict the claim. Yes, it contradicts because it is on the outside of the 99%. So the hospital's saying 5.7, but we're 99% sure it's between 3.5 and 5.4. Make sense? If you can do this one, you can do any of them. We'll kind of keep looking through some of these, but they all work the same way. Oh, this is something that I need to talk about for a second, I think. The T distribution. All right. So you know the chart that looks like that we've been dealing with, the normal curve, and we talked about Z-scores, right? The T distribution is the same exact thing as Z-score, but if you are sampling less than 30 people, it's better to use a T distribution than it is a Z-score. I do not think that you actually have to know that for any of your problems. So I'm just saying that. I think it's the way I have it set up is not. It's kind of weird that the way it works. Basically, they should just use T for everything because after 30, T and Z start to be the same. But under 30, when you're sampling under than 30 people, T and Z have a little bit of difference. So we'll see as we work these problems over the next week if we actually need that information. But I just want you to know, when you see something about a T, it's like the Z. It's like a Z-score and T-score, okay? They work the same way. The T-score technically used when in Z or when N is less than 30, but in your brain, it should do the same thing, okay? So when I do this, to find this, it says T equals 1.25 to the right. So I'm going to use the T1, 1.25. Oh, what's my answer here? Let me make sure before I. Oh, it says it right there. Sorry. So this T button right here, I was reading the question wrong as well. I got the answer wrong the first time. It says the T distribution was 6 degrees of freedom. So that's what that with df equals. You are going to have to put that in there. The degrees of freedom, we're talking about small numbers, right? I said this is used for anything less than 30. So what this does at the degrees of freedom is it says we have small numbers to work with, and it's hard to work with small numbers. So if we only have 19, let's run all our numbers at 18 so that we have a little bit of freedom if we messed up, because there's so much variation when you have small numbers. So that's what the degrees of freedom is, and that is actually what the degrees of freedom is n minus 1. You always do n minus 1, 1 less than the number that you sampled, so that you have a little bit of numbers. Like I said, if we're running a sample and only got 12 people in it, well, I'm going to run all my calculations with 11 people, because that will give me some freedom is the best word to use there, if I did something wrong. I don't think this one will ever do anything to the left. These are all to the right so far. So yeah, all you have to do is click this button and do negative 0.5 with degrees of freedom of 10 and get your answer. Okay. So all you're doing is using this button right here. If it does ever do to the left, how do I flip the sign in the calculator? 1 minus. Everything works the same way. Okay. All right, so now on these confidence interval ones are going to start using the T distribution. Oh, wait. Sorry, we got to do this one first. Another one. So this one does the opposite. You can kind of tell by the way it's labeled right here. Can you all see that? The T subscript 0.9. That means you're going to use this button on the calculator, the T box. So I do 0.9. Degrees of freedom would be 9. Whoa. Click there. And that should be my answer. Okay. So this one, what you're actually doing here is they give you the area, and you're trying to figure out what the T-score that goes along with that is. So like this one, I would click T-score, 0.03. Degrees of freedom is 8. But everything kind of works the same as like the Z-score. It's just a different button. So my Z-score that gives me 3% to the right would be 2.189. If, let's say, this problem right here, let's say we wanted to actually find, let's say we wanted to find, this is 25. It kind of gives away the answer though. That's fine. What if I wanted to find 75% to the left? This calculator only gives me to the right. Never mind. It's the same number. 75% to the left would be the same number as 25% to the right, right? That would give you the same number. Okay, they're never going to make you go to the left, so we'll talk about that if it happens, but it's not going to happen, so we're not going to worry about that right now. All right, now, I forgot about that one. Now you are going and doing a confidence interval with the T. So again, the big difference here you're going to notice is I don't have more than 30 drafts to sample. I only have 13. So these numbers are all going to be less than 30. But to you, as you're doing these problems, it doesn't really change your answer at all. 1.492, or it doesn't change your process at all. Okay, what's my confidence interval? 95%. This one gives it to me. 95% would be 95% on the inside, so 5% on the outside, 2.5 on each side. That's why it's 0.025. You're going to have to do that on the next one. So we click compute. Yeah, I mean, the process of this with the T-score does not change at all. That's what I was saying about the hypothesis testing, but it's the same thing with these. Once you figure out how to do one of these, you kind of figure out how to do all of them. All it's really doing is changing the process in the background. You're using Z instead of T. But most things in real life kind of calculators online change that for you anyways. Let's see, we've got 2 left here. So let's make sure we got this. Sample size, what we're doing, sleeping. How much sleep did they get before test? Before finals? 16 students, slept an average of 6.741. Sample standard deviation, 1.609. 95%. So can somebody tell me, if you need to break out your phone calculator, you can use it. Tell me which T-score to use. This is like the hardest part on these problems. .131. Yes, you would do if you forget. There's 95% on the inside, so there is 5% on the outside. Divide it by the two tails, 0.025. Okay. So that is 2.131. Yeah, I mean, this really is nothing different than what we've been doing, but we can finish this problem real quick. Might as well do them all. That's a pretty small 6.6553. Did I do something wrong there? Oh, I put a 0 in there. Thought that was small. 5.884. 7.598. But they're claiming that students get about 7.05. So they're claiming that students get about 7.05 hours of sleep. We're 95% confident that they get between 5.88 and 7.6. So no, we did not contradict the claim because it is inside. It does not contradict when it's on the inside. It does contradict when it's on the outside. So these two right here you never use. You always use A or D. Okay, one more just to make sure it's nothing different than what I think it is, but I'm pretty sure it's just the same thing that we've been doing. Oh, this one has to do with percentages. So there's always like the same thing on hypothesis testing. We'll do the same thing. You do the mean when it's over 30, so you use a z-score. You do the mean when it's under 30, so you use a t-score. And then we do the proportions. Proportions are just percentages, right? Okay. So the website of a large corporation, Corp Plus, claims that 93% of its employees, of the population of all employees, say the corporation is a great place to work. So we do a sample of 55, and we find out that only 80% of them say that it's a great place to work. So how many people did we survey? We surveyed 55. We're saying that 80% of them say they like working there. Our critical value, somebody tell me the critical value. Just like I said, it's hard. This is the hardest part, choosing which one of these. 1.645 is correct. If you forget, 100% minus 90%, that means there's 10% on the outside, divided by 2 for each tail. So 5.05, 1.645. And now we do this. So it's 80%. Oh my goodness. 80% plus or minus 0.089. Oh my goodness, my margin of error is almost 9%. Okay. So then we have a small number to work with here, or a lot of variation or something. 0.711, 0.889. They claimed it was 0.93. Okay. So we would say, yes, we do contradict the company. They said 93% of the people like to work there, but we are 90% confident that only 71 to 89% like to work there. Okay? Make sense? A little bit?